Welcome. Today we're going to be talking about the octet rule, valence electrons, ions, and naming ionic compounds. Let's begin with valence electrons. The valence electrons are incredibly important because they determine the chemical properties of the elements. And so all the chemical reactions, all the behaviors we're going to see in this chemistry class are going to be the result of changes and interactions with these valence electrons. And so these are electrons that are outermost or in the highest energy level of the atom. And what that means, if we sort of translate that into common language, is that the electrons are on the surface of the atom. So all the electrons on the surface of the atom, the outside surface, they're going to be responsible for the behavior and the chemical reactions of the atom. And you might be wondering, well, how do we determine how many valence electrons we have? Well, we do that by looking at the group number. Groups are commonly numbered two different ways, but the numbering system that uses the A's is the system we're going to focus on here. And so in order to determine the number of valence electrons in the A numbering system, the valence electrons will match the group number. So group 5A has 5 valence electrons. Group 2A has 2 valence electrons. Group 6A has 6 valence electrons, and so on. And you guys are wicked smart, so I'm sure you're already seeing the trend there. The group number just matches the valence electron number. We do have just one exception to the rule, and that one exception is helium. Helium's at the top of group 8A, yet it only has 2 valence electrons. All the other elements in group 8A have 8 valence electrons, but helium just has 2. And all the other elements will match the A numbers except for helium. The B groups, don't worry about those for now. They're much more complex, and so don't worry about the number of valence electrons for those. We're going to focus on the A groups. We're going to use this idea of valence electrons to talk about the octet rule. And so the octet rule states that 8 valence electrons is the most stable configuration. In other words, all the elements are going to share or exchange electrons in order to try and match the nearest noble gas, because the noble gases have 8 valence electrons. And so if we take a metal and we combine it with a nonmetal, we're going to end up with transfer of electrons. So metals and nonmetals transfer or exchange electrons, and we form an ionic bond. And an ionic compound results. And if we take nonmetals and we combine them together, nonmetals are actually usually going to share electrons with each other. And this is going to result in formation of a covalent bond. So I'd like you to now pause the video and then please complete questions 1 through 3 on the worksheet. Welcome back. So we mentioned that we can either share or exchange electrons in order to satisfy the octet rule. Today we're going to be focusing on exchanging, and next week you'll be taking a deeper look at sharing of electrons. So what happens when we take a metal and we react with a nonmetal is the metal is going to lose valence electrons. And so group 1A, these are going to form 1+ ions typically. So like sodium, potassium, lithium, those elements like to lose electrons to form a 1+ charge in order to satisfy the octet rule. And then elements in group 2A like to lose 2 electrons, so they're going to form a 2+ charge, and the metals in group 3A like to lose 3 electrons to satisfy the octet rule, and like to form a 3+ charge. So essentially we can predict the charge of a metal based upon its group number oftentimes. And also another takeaway message here is the fact that metals like to lose valence electrons in order to be satisfied. And so here we have a specific example. An atom of magnesium has 12 protons and 12 electrons. We know that we have 12 protons because if we look at the periodic table, magnesium is number 12 on the periodic table. It has atomic number 12, which denotes 12 protons. And we also have 12 electrons because that term atom means that our protons and our electrons are going to be equal to each other. And we have an overall charge of 0 in any atom. So again, in any atom, protons will equal the electrons, and our overall charge will be 0. Now, if we have a charge present, this is referred to as an ion. And so magnesium is going to keep those 12 protons, but it's going to want to give away some electrons. And so we form this magnesium with 10 electrons, and this one has a 2+ charge, this magnesium ion. And so why 10 electrons? Well, if we look at the periodic table, neon is number 10 on there. So what the magnesium's doing is trying to get the same number of electrons, the same electron arrangement as neon, because that's the nearest noble gas. Nonmetals are going to tend to form anions or negative ions. So we tend to form charged ions called anions from these nonmetals. And so the metals form cations, the nonmetals form anions. That's how you pronounce those terms. And so elements in group 7a like to form a 1- charge because they have just to gain one valence electron to match the nearest noble gas. Elements in group 6a like to form a 2- charge, and elements in group 5a like to form a 3- charge. Looking at a specific example over here, we have chlorine. And so an atom of chlorine is going to have 17 protons and 17 electrons. We know that because chlorine is good old number 17 on the periodic table. And so our overall charge for any atom is going to be 0. But the chlorine is going to want to gain an electron. If we look at the periodic table, number 18 is argon. So by gaining an electron, it has the same electron arrangement as argon, and it becomes extra stable. And this is how it satisfies the octet rule. And so we call this a chloride ion. This chloride ion has a 1- charge. I'd like you to now pause the video and please complete question number 4. Welcome back. Alright, so one of the things you'll be asked to do in this chapter is to convert from name to formula and formula to name for ionic compounds. And here we have some rules to help us name ionic compounds. The first is we want to identify what cation and what anion is present. Now this is pretty easy to do because in the formula, the cation is always listed first, the anion is always listed second. So it is always going to be listed positive ion followed by negative ion. So that's going to help us identify which is which. And when it comes to naming the cation, it's pretty easy. Those are usually going to be metals, and the ion has the same name as the metal. So the cation, or the positive ion, is named by its element name, which again is usually going to be some type of metal. And the anion we're going to name using the first syllable of its element name followed by "-ide". And to write the name of the compound, write the cation name first, followed by the anion name. And so this is complicated slightly because we have a number of metals that form multiple charges. So the transition metals form a bunch of different charges. And so we have a naming system that's used to indicate which charge is present. So for instance, we can't just say a chromium ion, because we actually have two different common chromium ions. There's more actually, there's several chromium ions, but our two most common are chromium 2+ and chromium 3+. So chemists came up with a simple way to name these and distinguish between them. We still call them chromium, but we use this Roman numeral 2 or 3 to indicate the charge. Copper, for example, forms both +1 and +2 ions commonly, and so we'd refer to that as copper 1 and copper 2. So again, we use these Roman numerals to denote the charge on these metals. So if you're naming a compound that has a transition metal in it, remember to include that Roman numeral in the name to indicate that charge, and don't include the Roman numeral in the formula. I'd like you to now pause the video and please try and complete questions number 5 through 7. And so if you're running into problems, you're finding this really difficult because the naming is really challenging, people tend to need a lot of practice with this, then what you can do is maybe post some questions up in the discussion board. So if you're struggling with a problem, post up in the discussion board, and hopefully some students will interact and you'll get some assistance there. All right, welcome back. We have another complicated situation to talk about, and that is the polyatomic ions. So there's many polyatomic ions, but I'd like you to memorize this list right here. So this list of polyatomic ions, and I have the same list posted in Canvas in the module. I want you to memorize these polyatomic ions, and that includes the name, the formula, and the charge. And I know memorization's a pain in the butt, but this is really important. I've picked several ions that are extremely common in chemistry and also really relevant and important in biochemistry, so you really must memorize these because they're going to be important. And of course, you're going to be tested on them. So When it comes to naming the polyatomic ions, if they're in your formula, you just stick the name for the polyatomic ion in for when you're naming the ionic compound. So I'd like you to now pause the video and please complete question number 8 on the activity. Welcome back. We are almost finished. Let's take a look at some example problems. But before we do that, let's talk about formulas for ionic compounds. So again, you might be asked to go from formula to name or name to formula. So important things to note about the formula for an ionic compound: the amount of positive charge always has to equal the amount of negative charge. So essentially we're looking for the smallest ratio of positively and negatively charged ions that are going to cancel out or have their charges sum to 0. So again, our total positive charge must equal our total negative charge. So for example, if we're asked to write the formula for a compound containing sodium ions and nitrite ions, sodium's in group 1A, so sodium likes to form a +1 charge, and nitride's in group 5A, so likes to form a 3- charge. And what we'd see is we'd actually require 3 sodium ions to cancel the 3 units of negative charge on that nitride. So our formula here would be Na3N. And so again, our formula is always going to be, for an ionic compound, the smallest ratio that's going to contain equal amounts of positive and negative charge. Moving on to another example, we're asked to write the formula for copper 1 nitride. So copper 1, the charge on that is 1+. How do we know that? Well, copper is a transition metal, and we can't predict that from its periodic table location like we can with most of the A group elements, but our clue here is the 1. So the Roman numeral 1 in our name there tells us that our copper has a 1+ charge. Nitride's in group 5A, so it likes to form a 3- charge. And so what that means is we'd require 3 of these coppers in order to cancel the charge in that one nitride. So our formula here would be Cu subscript 3 N, because again, we're always looking for that smallest ratio where we have equal amounts of positive and negative charge. Let's see how we did. Oh, their version's much prettier than mine. So congratulations, you made it through. I'd like you to now end the video and please complete question number 9 on the activity. Great job. Bye.